Okay, so I want everybody to start off with an exercise, just to remind yourself of what we were doing last time. Try to explain why it's true that if A is invertible, that's the same thing as saying that the columns of A are linearly independent. Linearly independent. Why is that the same thing? So if you understood what we were doing last time, then just remember it. Okay, talk to somebody if you have not already.
That's the case.
Okay, would somebody like to say what the main points are? Like, why does this happen? Well, A being invertible, what does that have to do with columns being linearly independent? Who would like to say? Anybody? Anybody? Montana, go ahead.
Does it have to do with when you reduce it to the echelon form, you don't want a column with zeros?
Well, when you reduce it to row echelon form, you wouldn't get a row of zeros.
Right.
You wouldn't get a row of zeros. So that's different from saying that you wouldn't get a column of zeros. Although you could say A is invertible if and only if A transpose is invertible, right? And so, so yeah, actually you could argue in this way, yeah. You'd say, well, look, A is invertible if and only if A transpose is invertible. But that means that when you do the row reduction, you do not get you do not get a column, a row of zeros, right? Right, you get the identity matrix when you do the row reduction of the transpose, right? So that's basically saying that you can't express one column as a combination of the other columns. You can't express one column of this guy as a combination of the other columns. Right, which is the same thing as linear independence. Okay, I think it's a little bit easier to argue in a different way. Mariah, maybe you were going to say it.
Like after the limit of A is invertible, then like AX equals 0.
Yeah.
Yeah. So then you know unique solutions x equals 0, so like all the coefficients have to be.
Okay, exactly. So it's maybe more strict. That what you're saying is perfectly true, Montana. But I think it's probably easier to say this: that A is invertible. Remember, is equivalent to saying that the system AC equals 0 has only the trivial solution, right? In other words, where you take C to be the 0 vector, right? A being invertible is equivalent to this thing having only the solution where C is just a 0 vector, right? But that's the same thing as saying that C1A1 plus C2A2 plus CNAN equals 0 has only the solution with C1, C2 up through Cn all being equal to 0, right? Which is linear independence, which is exactly linear independence. Right, so invertibility, because we showed it's equivalent to this thing basically is linear independence. Okay, so that is something that we finished up with last time. That A is invertible if and only if its columns are linearly independent. And you see that because the transpose is invertible if and only if the matrix is invertible, you see that the rows will also be linearly independent, right? So A is invertible if and only if its columns are linearly independent, if and only if its rows are linearly independent. So those are all the same thing. Okay. Any questions? Okay, so let's go on to the next section, 3.4, basis and dimension. Okay, we start off with a thought. So think. Suppose you have a vector space. Suppose you have a vector space, and suppose you have a set VI that the span of VI is all of V, and the VI are linearly independent. Suppose you have the set and it has these two great properties, that the span is all of V and the set is linearly independent. So remember what we said about linear independence last time. Remember, if you're linearly independent, then anybody in your span can be expressed uniquely as a linear combination, right? Let me hold on. People are writing. You guys are faster writers than the other class. Still shouldn't rush it. Okay, so remember what we said about linear independence, right? Linear independence is equivalent to this property that everybody in the span has a unique expression as a linear combination, right? Everybody in the span can be uniquely expressed as a linear combination of these guys. Okay, so if the span is the whole set and you're linearly independent, that means everybody in the space can be expressed uniquely as a linear combination of these guys, right? So notice that every vector in your space can be uniquely expressed as a linear combination of the VIs. Right? Everybody has a unique expression, right? Each one corresponds to some combination of these vectors. Okay. And so this is the thing that we're hoping for. What we do is we associate that vector with the unique coefficients that go with it. Okay, right? The linear combination has these coefficients on it, right? It'll be like something like, like C1 V1 plus C2 V2 plus blah 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 CFDN. And there's only one combination that works for this guy. Okay, and so what we're going to do, not today, but in the next class, is say to each vector we're going to associate a coordinate, right? A set of coordinates, C1, C2 through Cn. Okay, so you start off with your abstract vector space, right? You have your abstract vector, but it's associated to this set of n numbers. Okay, and this will give us a coordinate system for the abstract vector space. Okay. In some sense, in a very real sense, it takes your vector space and says, oh, it's basically the same thing as Euclidean space. Right? Euclidean space, every point has these n numbers. Now what we're saying is that for an abstract vector space, you can do that too. Right? Every vector in the abstract vector space is just n associated with n numbers. Okay. So so let's this sort of prompts the important definition of a basis. So definition. Again, you start off with V, a vector space. And the VI's, a set of vectors contained in V. So if the span of the VI's is all of V, and 2, the VI's are linearly independent, then we say that the VI's are a basis. Okay, or a basis of V. Okay. A basis of that vector space. Okay, so let me give some examples to make this concrete. So a very simple example, right? Suppose your vector space is R2, right? Give me some vectors that are linearly independent and whose span is all of R2.
0, 1, 1, 0.
0, 1, 1, 0, right? So this guy and that guy, right? They're linearly independent and their span is all the whole space, right? So these guys are a basis of R2. Okay. Right? Or if we're looking at, say, P3, the polynomials of degree strictly less than 3, right? Then what's a natural basis for this? Don't blurt it out. What's a natural basis for the polynomials of degree less than 3? Give me 3 guys whose linear combinations make up all these polynomials. Ethan?
0, 0, 1.
So these are the polynomials, right? So things that look like 5 plus 2x plus 3x squared, stuff like that. Right? So give me 3 things that Montana?
Like x cubed plus 0 plus 0, x squared.
We don't want x cubed because there's nothing of x degree 3.
Oh, okay.
Right, so
it would be x cubed, x and 1.
x squared, x and 1.
Squared.
Yeah. Yeah, so 1, x, and x squared will do, right? These 3 polynomials, right? We've got one vector, another vector, and another vector, And these three guys, are linearly independent, like we said last time, because of Taylor's theorem saying these guys are linearly independent, and their span is clearly all of the space. Right? So these guys are bases of P3. Another example is a couple classes ago, we took a matrix 1, 0, 5, negative 3, 0, 1, 2, negative 1, and we saw that the null space of this thing was the span of two vectors, right? Negative 5, negative 2, 1, 0, and 3, 1, 0, 1. Right? The null space was the span of these two vectors. Right? This subspace was the span of these two vectors. So clearly these two vectors span it. Are they a basis? Are they also linearly independent? Are they independent of each other? Is anybody in the span of the other? Is this guy in this guy's span? No, right? Because you can't, right? You've got this 0 here, right? To get that 0, you have to multiply the whole thing by 0, right? These guys are linearly independent, right? You can't get this guy as a multiple of this guy. Okay. So these are linearly independent, and so these two vectors are a basis of the null space. Okay. So I hope you're getting a sense of what a basis is, right? Basis is this, it's a bunch of vectors whose linear combinations give you the whole space, and they are also independent. They are also linearly independent, right? So when I throw in this guy here, then it's no longer a basis, right? No longer a basis because they're now dependent. Mariah, what is it?
I think I was just trying to remember.
How we did this?
Yeah, but it's okay.
You just
You add the zero.
you say like x1 is negative 5
Yeah.
x3 plus x4 blah,
Okay,
blah,
yeah.
blah, 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 blah.
Oh, okay.
Okay. This leads us to the following definition. Suppose that V is a vector space again, and suppose that VI is a basis. We define this thing called dimension. The dimension of the vector space as the number of elements in VI. So this, when you write this number sign, it means the number of elements in. Right? It tells you how many elements are in your set. It's, another more formal term for it is the cardinality. Cardinality of a set, right? The number of elements in a set. Okay, so coming back to here, So coming back to here, right? You see that this thing has two elements, and the basis has 2 elements, so this is 2-dimensional. The basis has 3 elements, so this is 3-dimensional. Right? The basis has 2 elements. This subspace is 2-dimensional. Okay, so that's how we define the dimension. Okay, so this is one way of defining dimension in mathematics. Yeah.
I was pretty much just said about how the dimension of the example right there, of 1.
This one?
Yeah.
Yeah. So you just take a basis and you count the number of elements in the basis.
Oh.
Well, there's 1, 2 elements, so we call this thing 2-dimensional. Right?
Okay.
The plane is two-dimensional. And this sort of goes in line with your sense of what dimension ought to mean. Right? If it's the line, right, then you see that you can take the number 1, right? The number 1, everything is a multiple of the number 1, and this thing is one-dimensional. It has a basis consisting of this one thing. Right? Yeah. So it sort of lines up with your notion of what dimension means. Come on, Dan.
Will all vector spaces R to the n be n-dimensional?
Yes. Yeah. So R3 is 3-dimensional, R4 is 4-dimensional, etc., etc. Okay. So I want you to look at this definition and tell me if there's something unsatisfactory about it. The first class, actually, some guy, even before I said this, was saying, but, and he caught it almost immediately. There's something wrong here, something troubling about this definition. Montana.
You can add the 0 vector and sometimes.
No. Because if you add the 0 vector, then your set becomes linearly dependent immediately, right? So you can't just throw in the 0 vector. So no. So it says, in order to figure out the dimension of a vector space, you take some basis of it and you count the number of elements in that basis, and that's your dimension. Laura.
I mean, wouldn't they be different?
Right.
Yeah.
Right. So how do you know that all the bases are going to have the same number of elements? Right? Why are you guaranteed that all bases have the same number of elements? Okay. So you don't know that. We actually have to prove that. So we need to show this definition is not well defined. In that we don't know, we need to show that all bases of the same vector space have the same cardinality. Since I told this story in the first class, I'll tell the story in the second class as well. So when I was an undergraduate, I had a friend, also a math major, but he was taking a physics class. And in that physics class, they were dealing with some infinite dimensional space. And the professor had given a basis for it. And then he said, okay, now we're going to switch to this other basis. And he put up this other basis. Now the thing was that the first basis had an infinite number of elements, and the second basis had an infinite number of elements also. But those were two different kinds of infinity. One was what's called a countable infinity, the other is what's called an uncountable infinity. Okay, and so it's two strictly different kinds of infinity. And so this enraged my friend, and he leapt to his feet and started shouting at the professor and became famous, in the school forever. Okay. Yeah. Unfortunately, he became a lawyer later on. Yeah. I mean, it's really unfortunate actually. He got his degree at Harvard, I think. Yeah, he went to Harvard afterwards. But then it's actually in order to support his family, he became a lawyer. Yeah, his family, he had basically lost his family, and his family showed up, and he had to split them. Okay, so let's show that this thing actually is well defined using the following theorem. Okay, so here's what we're going to use. Sort of an odd thing. Suppose you have V1, Vn, and and that set spans V. And suppose that there's some number that's bigger than n. If you have another set, U1, BUM, of that size that is bigger than the size of the spanning set, sorry, let me say it this way. Any set of vectors, U1, BUM, must be linearly independent. Linearly dependent. Okay. So you have a vector, you have some vector space, and you have some set that spans it. Okay. You have some set whose span is the whole vector space. Any set that has more elements than that must be linearly dependent. Any set that has more elements than the spanning set must be linearly dependent. Okay. That's sort of believable, right? If I'm in R2 and I've got a spanning set, right? Here's basically my minimal spanning set, right? And I have more than that, well, then there's going to be some dependence. Okay? Right? That seems cool. Yeah, Mariah.
And it's only for like a specific vector space, right? It's like for a vector space.
Yeah. So let V be a vector space. Start off with a vector space, and suppose you have a spanning set of it. Okay. You have an arbitrary vector space, you have a spanning set, and you have a set that's bigger than, whose cardinality is bigger than that of the spanning set. Well, that bigger set must be linearly dependent. If we state this as its contrapositive, it actually works a little bit cleaner. You say if U1 to UM is linearly independent, then M must be less than or equal to M. In other words, cardinality of a linearly independent set must be less than or equal to the cardinality of a spanning set. Yeah, Joel.
So can you describe like a three-dimensional space with like less than 3 bases?
Right, so that's what this is saying. What we're going to see is that any three-dimensional, if it's three-dimensional, that means that all the bases have to be, you have to have three elements. Right? Any bases of any bases will all have the same number of elements. Okay. So you know it's impossible. Like you couldn't have like 2 elements that somehow span your set. That'd be impossible. I should say, I don't know, I should say, I want to say that when I was an undergraduate, there were all sorts of crazy people, right? And so there'll be stories about all, like, our classmates all the time, or like professors, they're eccentric professors, eccentric students. I'll tell you 1 or maybe 2 stories, just for fun. So there's one professor, the number of students in a class, in an upper division class, could be very small, like 3 students. And sometimes I was in a class with only 3 students. We heard one story about one professor that one day one of the students came in 20 minutes late. She was late to class, and she found the professor was there lecturing for 20 minutes to an empty classroom. And it wasn't clear to us that if he had not noticed that there was nobody in the classroom, or if he had done it just to say that he had actually done this lecture and the students should better know the material. But anyway, he had been lecturing for 20 minutes to an empty classroom. And I've always said that that's sort of my dream to do that, but now with the camera, it sort of invalidates the humor. Right? It actually, that it would actually have a function. And to tell you another kind of cool story, so everybody was always trying to do something cool, right? And there's one of my classmates who was always kind of trying to come up with some theorem or something that he could prove. And so he thought of something and he checked it out. No, this is a different story. He thought of something and he said, okay, I've thought of this idea, but don't tell so-and-so. So-and-so was another math major in our class. He was like, really, really smart. Unfortunately, somebody leaked the theorem to so-and-so. And by lunchtime, so-and-so had already proven it in two different ways. So, yeah.
Wait, what happens when you come up with like a new theorem? Like you like publish it?
You can publish it, yeah. You can get it into some journal or something like that.
So who gets it then? You come up with a theorem?
The person who solved it. Yeah. And it's kind of a terrible thing because you could be a PhD student working on a problem, and then suddenly so-and-so so-and-so student at some other university publishes the paper, and then your 5 years of work is all gone, right? Then what do you do? Right? No, this is a very definite possibility. Right? That would be the end. Right? Unless your method is completely different from the others, but even if it were, it wouldn't be that significant anymore. Right? Your PhD, your thesis, your dissertation is gone.
So you get a PhD, you have to come up with and prove a new theorem?
Yes, new and significant. Something that nobody has ever proven it before, and it has to be significant. Right?
Do you ever think we'll run out?
No, because the edge is always expanding. Right? So no, but you can see the kind of stress that that people are under as math PhDs. Yeah. That's why we're all a little crazy. Okay. Yeah. But then sometimes there are nice people too, right? Like there's a professor at the University of Chicago. I think he had proven a result, but then he heard that so-and-so student somewhere was working on this problem, and so he just said, I don't need to publish this, so I'm just the back. Yeah. Okay, so, so we all your professors have gone through that. Gone through that kind of miserable.
Can you eventually tell us the theorem that you proved?
It would take a couple of days at least. Yeah, because I'd have to set the background for it. I've tried it in a class before. They didn't like it. Yeah, it's hard. Okay. So let's get on with it. Linearly independent sets must have a cardinality less than or equal to that of the spanning set. Okay. Now, so suppose the corollary is that all bases, right? If V is a vector space, and V1 and Vi and Ui are bases of V, then M must equal N. Okay. Does anybody see immediately why this is true? Think. If you're a basis, then you are linearly independent, and you're also spanning. You're both of those, right? Right? So each of these is linearly independent and spanning. This guy is linearly independent, this guy is spanning, this guy is linearly independent, this guy is spanning. we just said the size of a linearly independent set is less than or equal to the size of a spanning set. In other words, n must be less than or equal to m, right? Because this is linearly independent and this is spanning. But this is linearly independent and this is spanning. So m must be less than or equal to n also. So, right, so by the theorem, we know that m is less than n and n is less than m, less than or equal to m. So they must be equal. Montana.
How do we prove for the contrapositive that m has to be less than or equal to n?
Well, so the forward statement is if m is bigger than n, and you have this set of vectors, then these guys must be linearly independent. So the contrapositives, you negate you negate this thing and you negate this thing, and you put them in opposite order, right? So if these guys are linearly independent, then m must be less than or equal to n. Like contrapositive, right? You have one statement, A implies B, that's equivalent to not B implying not A. Okay, so
we didn't prove that they must.
we haven't proven anything yet.
Okay.
We haven't proven anything yet.
Okay.
So we just say, here's this theorem, here's its contrapositive, here's its consequence, but we haven't proven the theorem yet. Right. Once we prove the theorem, we have its contrapositive. Okay, let me hurry up because we've only got 10 minutes left. Okay, too many stories. Okay, so here's the proof of the theorem. Proof of the theorem. Right? We want to show that these guys, the UI, are linearly dependent. In other words, we want to find C1 through Cn, m, not all 0, such that C1U, C1U1 plus C2U2 plus CMUM is a 0 vector. Right, that's our goal. Okay, so you say, well, look, each UI can be expressed as a linear combination of the VI's, of the VJ's. Right? Because the V's are a spanning set. The VI's are a spanning set. Right? So the UI's are linear combinations of the VJ's. Okay. Now consider C summation CIUI. That's the same thing as summation CI AIJ VJ. I just substitute in, I substitute in this. Each of the UIs is this, so I substitute that in for the UIs. Nothing amazing. Right? The VJs are a spanning set, so each of the UIs is expressible as a linear combination of the VJs. Okay. And so you say, okay, now I'm going to change the order of summation. I'm going to sum over the J's first rather than the I's. And I get CI, oops, let me write it this way, AIJ, CI, VJ. Okay, maybe I put it inside first. I'll put the VJs inside, but you notice that I can factor the VJs out by the distributive property, right? Because they don't change as I changes, the j doesn't change. So I can factor that out by distributed. Okay. Now, notice that the system summation aij ci equals 0, I equals 1, and as j goes from 1 to n, is a homogeneous system with m unknowns and n equations. Right? M unknowns and n equations. Observe. Right. This system is a homogeneous system with m unknowns and n equations. Right? And m was bigger than n. M is bigger than n. So you've got more unknowns than equations in a homogeneous system, and so you have infinitely many solutions. Right? So there are infinitely many solutions. Right? Choose a non-trivial one. Right? So C1 to Cm, not all 0, such that these things always equal 0. But then you've got that this thing equals 0, right? You've got a linear combination that equals 0. You've got a non-trivial linear combination of the ui's that equals 0. And summation ci ui from I equals 1 to m equals 0. So the ui are linearly dependent. Yeah, sure.
So would you write like, so is it choose a non-trivial one, then C1, Cm, all 0, what's that S down?
Sorry. Such that.
Oh, such that.
Okay. So what you see is that if these guys are linearly, if you have more elements than in a spanning set, then you must be linearly dependent. If your set has more elements than are in a spanning set, then you must be linearly dependent. Okay, we have a couple minutes left. Any questions about this? This is not a particularly exciting proof. It's sort of like, you say, well, look, we're trying to make this thing equal to 0, and lo and behold, making that thing equal to 0 boils down to, can we solve this system of equations? This system of equations is a homogeneous system with m unknowns and n equations, where m is bigger than n, so yes, you can. Okay, that's the outline of the proof. Right? The question of, can you find a non-trivial solution, boils down to, can you find a non-trivial solution of this? And you can. It's not a very insightful proof, I would say. So if it seems kind of like a lot of calculation, that's basically what it is. Okay, let me get to the last part, last theorem in this section. So it's this. Suppose that the dimension of a vector space is n. Suppose you know from the beginning that you have a vector space and its dimension is n. Then, if you have a set has n elements, it is spanning, it is linearly independent, if and only if it is spanning. So what this is saying is that if you have, if you know the dimension of the set already, the dimension of the space already, and you have a set with n elements, to show it's a basis, you only need to show one of these things, right? Because if I prove this, I get the other. If I prove this, I get the other, right? Normally, when you need to prove a basis, you have to prove both of these things. But if it's the right size, you only have to prove one. If your set has n elements where n is the dimension, you only have to prove one. Okay. And so I think this basically as an exercise for you guys. Try and think about it. I've got no time to do it. So maybe I'll just sort of lay it out for you. So do it by contradiction. Right. Suppose that the VI is linearly independent, but not spanning. Suppose it's linearly independent, but it's not a spanning set. Okay, why would that be a problem? If this linearly independent set, there's n elements in the set, it's not spanning though. Why is that a problem? That's a problem. So think, if it's not spanning, then there's somebody in the space that's not in the span, right? So we know there's some vector that's in the space, but it's not in the span of the other guys. I'm going to introduce this notation. It's in the space, but it's not in the span, right? So it's in the space, but V is not in the span of the other guys. Since we don't have time, I'm just going to say it. Okay, so what you do is you say, well, look, then I throw that guy into the set. Okay. In that case, then VI, maybe let me call this guy Vn plus 1. If I throw that guy in too, is a linearly independent set. Right? Because this guy wasn't in the span of the other guys. I throw him in, he's still, these guys are still going to be linearly independent. Okay. But then you have a linearly independent set with n plus 1 elements. Right? But the dimension of your space was n, right? So that means that this n plus 1 must be less than n, right? Because you've got this, you have a basis which has a spanning set, has n elements, right? So this linear independent set must be smaller in cardinality than the basis. So n plus 1 must be less than n. That's a contradiction. The cool contradiction symbol. Okay, and then the opposite direction is kind of the same sort of thing. Okay, that's it for today. That's it for today.